check, check. Okay, let's begin. So, what do we have going on? Oh yeah, I moved the due date of homework 6, is that what we're on? Homework 6, to Friday of this week, basically to accommodate the calendar. Don't take this as any kind of precedent that we're now extending due dates on homework, right? The way I do it on programming assignments. Programming assignments, I consider those due dates to be kind of movable and flexible. Homework, not. Okay, the only reason I moved it this week is because we lost a day. So I'm going to try to get back on track to having it done Wednesdays as of next week. The reason I want to get another one posted, I guess I should post that one now then, right? That should be posted already. Homework 7. The reason I want to get that one done and finished by and turned in by Wednesday is I want you to see the solutions before Friday of next week. What's Friday of next week, you ask? Second midterm. Okay, so I consider all these homeworks and their solutions to be nothing but practice for the midterms themselves. And that's why it's important to keep those on track. Okay, that's what to expect in the near future. You're not going to get your homework 5 back until Friday. It'll be graded on Friday and turned back here. Okay, programming assignment 4 is due this Friday, right? Okay, it seems a little soon, considering we haven't gone over BFS yet, but we're going to go over that today. I would expect, though, that everybody has been able to start building their graph ADT. So with the exception of the 2 algorithms we didn't cover, namely BFS and what's in the book is called print path in the book. In the project, it's called get path, I think. Those 2 functions, I wouldn't think you'd be able to, or necessarily be able to do them unless you'd read ahead. Everything else you should have been able to do by now, and that is to create a graph ADT with the suggested fields and write all the easy functions, okay, and do that in C. So that's kind of where I would expect somebody to be, about halfway through their graph ADT. And not have necessarily worked on the top-level client, which was called, I forget what it was called, FinePath or something like that. Okay, so I'll extend that, but let's talk at the end of today as to when it will do, how long it will be extended. What did we do last time? Last time we covered the standard representations of graphs. There was the incidence matrix, which required both the vertices and the edges to be labeled. In a way, this gives you the most detailed information about a graph. Every single connection between every vertex and every edge is encoded in it somehow. There's a directed version and an undirected version, and we looked at an example. And these two examples are kind of a running example. Then we looked at the adjacency matrix, which only requires that the vertices be labeled. Edges are then encoded as a 1, or the absence of an edge as a 0. 1 in ith row jth column if there's an edge from xi to xj, 0 otherwise. In the directed case, 1 from in the ith row jth column if there's a directed edge from xi to xj, 0 otherwise. So the directionality is also encoded in the 1 versus the 0. Notice that the adjacency matrix for an undirected graph is necessarily a symmetric matrix, is it not? It means that it's the same if you flip it along its diagonal, its main diagonal, upper left to lower right. That's because xi is adjacent to xj if and only if xj is adjacent to xi. So aij has to equal aji. So it's a symmetric matrix. Not true for directed graphs. I remember at some point somebody was asking about the notion of symmetry in a graph. This is the closest I can come to understanding symmetry in a graph. Undirected graphs are symmetrical objects. You can go, they're two-way streets. Directed graphs are not necessarily symmetrical objects because you have these one-way streets. Just because you can get from I to j doesn't mean you can get from j to I. Okay, so that's the adjacency matrix. Of course, we can consider our sparse matrix representation of an adjacency matrix, and that's as an array of lists. So you simply store in each of these examples, say this example, I would store this row as a 2-element list because there are 2 ones in it. I would store this row as a 3-element list, this row as a 3-element list, etc. So since the only possible values are 0 and 1, the only information that needs to get stored, we don't store the zeros, we store the non-zeros. And the only value is 1, I don't really need to store the 1, I just need to know what column it's in. The column it's in is exactly the neighbor. So this 1 represents an edge from vertex 2 to vertex 3, which exists because it's in row 2, column 3. Okay, so that brings up the adjacency list representation. It's nothing but our sparse matrix representation, but applied to the adjacency matrix. We don't need to store a pair, a column value pair. We just need to store the column number. And the column number is the label of the adjacent vertex. So adjacency row 1 is going to store the neighbors of vertex 1. Those are 2 and 3. If I go back to the original picture, 1 has 2 neighbors, namely 2 and 3. Okay. And likewise for the directed graph, the directed version. All right, well, that basically ends the handout on graph theory. There's one very interesting problem I gave you in the homework and that is also mentioned at the end of this handout, and that is a fact about maybe I'll mention it here. so this is more than an exercise, it's actually a homework problem that's due Friday, show that A to the power D, ith row jth column, where A is the adjacency matrix, equals the number of xi to xj walks in G of length D. Now, I talked to a couple of people in office hours about that. It can be done by a very nice weak induction on the parameter D. Notice the base case is D equals 0. D equals 0 implies A to the 0. What's that? That's the identity matrix. Identity matrix is 0 or 1. Well, let me write it this way. Identity matrix ith row jth column is 0 or 1. 0 if there is an if I equals I is not equal to j, thank you, and 1 if I equals j. And indeed, we're looking at walks of length 0. The only such walk is a trivial walk. Stay where you are and don't traverse any edges at all. The only way to get from I to j doing that is if I equals j. You're already where you need to be. If I is not equal to j, you cannot get anywhere along a walk of length 0. So the number of such walks is necessarily 0. Okay, so the base case is a triviality. That's nice. You might also check the case D equals 1. That's just the adjacency matrix itself. That's just encoding where the edges are. And those are walks of length 1, aren't they? Where the edges are and where they aren't. Those are walks of length 1. All right, so I just wanted to mention that you should work on that. I find that an interesting problem. And it's not a difficult induction. At a key point, you need to use the induction hypothesis and the definition of matrix multiplication. I give some hints in the handout, so I won't say any more than that. All right, so now let's go to chapter 22.2. And I don't have a handout on this. In fact, we've reached the end of my handout. Someday I'll have a handout on this. This is breadth first search. I'll abbreviate that BFS. Okay. Well, what does BFS do? Does the following. First of all, 1, it systematically discovers remember what the single source shortest paths problem is given, a graph and a source vertex. It discovers every vertex reachable from the source. The source vertex S in V. That's part of the input to the algorithm and input to the single source shortest paths problem. Now, what do I mean by discovers? We'll just see what that means. That's why I put it in quote. I mean, how does the algorithm discover something? 2, it computes delta Sx for every x in V. Not just the ones reachable from S, but from the, even the ones not reachable from S. Of course, in that case, the value of delta Sx is what if x is not reachable from S? What is that value? Not 0. Infinity, right? If you can't get from S to x, we defined its distance to be infinite. 3. Now, it's got to solve the rest of the single source shortest paths problem. Namely, it's got to find the actual paths, and at least one path from S to x whose distance is this minimum value. So to do that, it creates a BFS tree. That's what I'm going to call it. It's also called the predecessor subgraph. So that BFS tree, what is it? This is a subtree of G that doesn't necessarily include all vertices, but it does include all vertices reachable from S. All vertices reachable from the source S. And what is it about this tree? What's important about this tree? Remember, trees have the property that between any two vertices in a tree, there is a unique path. So the unique path from S to X, the unique in this tree from S to X is a shortest Sx path in G. Now, I should probably do this, shouldn't I? Would you be happier if I did this again? There. Is that visible? Is that legible? Sort of. Okay. So that's what BFS does. How exactly is that tree going to be encoded? We'll see. To do all this, each vertex in the tree has to have a certain attribute. They are, first of all, color of X. The color of X is white, gray, or black. White means undiscovered. Gray means discovered, but not all its neighbors have been discovered. Black means finished. The vertex has been discovered, and all its neighbors have been discovered. So those are going to be the meanings of those values of the color attribute. Notice I write it as an array. In the textbook, their algorithm writes this as x dot color. As if X is an object and color is one of its fields. But of course, when we do this in C, it's a little bit simpler if you actually have an array called color, in your graph struct. And the type can be whatever you like. I think int is a perfectly good type for this array. And you encode white, gray, and black as integers, maybe 0, 1, and 2. Okay, I'm just talking a little bit as we go about implementation in the C language. That's one attribute. Another is dx. This is the distance estimate. Distance from S to X. So, in other words, this is going to be delta SX. These fields don't start out being this, of course. It's the job of BFS to assign this a correct value. They all start out at infinite because we haven't discovered anything. As soon as we discover a vertex, we know how far it is from the source, and it will receive a value, and that value will be delta SX. I want you to distinguish between what delta SX is and what dx is. Delta SX is a mathematically defined quantity, right? It's the actual shortest path length from S to X. And there may be many paths that realize that shortest length. dx is actually a value in an array, and it's the job of BFS to put the right value there. Okay? And then the last one is P of X. This is the parent or predecessor of X. So when I say predecessor, this explains how we're going to store this tree, this BFS tree, mentioned in item 3 here. We store it by keeping track for each vertex that's reachable from the source of the vertex that I have to get to one step before this one. So P of X is the predecessor of X along a shortest SX path. Let me just say that again. You've got a shortest SX path. Well, there's some vertex you get to right before X along that path. That vertex is PX. It's also called parent because this BFS tree is a rooted tree. And if you draw it with the root at the top, and the predecessor is actually going to be the parent of a vertex. So these values, again, aren't known before the algorithm starts. It's the job of the algorithm to compute these values. So they start out as a neutral value, which we call nil. Okay, those are the attributes that are associated with every vertex. We also use a FIFO queue. Which I'll refer to as capital Q. All right, so you can see where you can use your list ADT in trying to implement all this. First of all, BFS assumes that the graph is represented by an array of adjacency lists. Okay, so those lists are going to be used in the adjacency list representation. You might as well use the adjacency list to implement this queue also, because your list has more functionality than a FIFO queue needs to have, right? Our list is bidirectional, and you can add and append to both ends, so you have more than enough functionality to, to emulate a first in, first out queue. I don't recommend, in fact, I don't want you to go try to make some standalone ADT called Q, or maybe import the Q example in C that I posted on the website a long time ago, and use that for Q. I don't want you to do that. I want you to just use the list ADT. All right, so knowing all that, maybe it's time to just look at the BFS algorithm. And rather than write it down, I already wrote it down nice and neatly. By the way, this parent field, the book, for some reason, decided to use the Greek letter pi. Pi of x is predecessor or parent of x. Okay, don't be confused by that. The Greeks have a perfectly good alphabet. We can use that every once in a while. But it doesn't mean pi, the number pi. Okay. And don't worry, I'll just include it like this when I scan the notes. All right, so the first thing we do is initialization. For all vertices, so look at the input. The input is G, and you should think of G as your graph ADT. Literally a handle or a pointer or a reference to a graph object. And what's under the hood is its adjacency list representation. So when I say adj, ADJ, that's the adjacency list. That's a list, right? That's the adjacency list at index x. The vertices are just simply integers, integer labels. Okay, for all x in the vertex set other than S, initialize them by setting color to white, distance to infinite, and parent to nil. Okay, that's the initialization. Go ahead. Does C, no, I don't think it has an infinity. So you need to, we're also talking about implementation details here. So you need to create a, a constant macro in your .h file, graph.h file, called inf. I don't know if I recommended this or if I required this, but you should do this. Create a constant macro called inf, and it should just stand for some integer, because the type has to be int, because it's being assigned. D is going to be an int array, so this has to be some int value. All that's really required, we're never going to compare as to size. So we just want to see if something's infinite or not. So what we want inf to be is some integer, some int value that can never be a valid distance from the source to x. Well, the only such numbers are negative numbers, right? There can't be a negative distance. So pick any negative number and let it stand in for inf. That will do fine. You don't have to, dream up something. You have to start digging into the C language for some representation of infinity. Okay, so we initialize white, infinite, nil. That's everything except the source has been initialized. Let's initialize the source to gray, 0, nil. Okay, so first of all, gray, because we start by discovering the source. We've discovered the source, but we haven't yet discovered any of its neighbors. That's why it starts out gray. The distance from the source to the source is, in fact, 0. So that's the right number. Right? So we've discovered that one. And in the BFS tree, there is no predecessor to the source. There's nobody you get to before you get to S in an SS path. Right? So that's why this stays nil. Okay, this is to initialize the queue to empty. You can think of that as the list constructor, right, which gives you an empty list. NQ, I guess you should use append for that. You could reverse it and use prepend if you like, because it is a bidirectional list. But I think of that as append. So push the source onto the back of the queue. The queue contains now just one element, namely the source. And we enter a loop. This while loop is where the real work gets done. This is the guts of the algorithm, this thing right here. Okay, while the queue is not empty, Well, there's something left in the queue. DQ. So you can, this is, I guess, the combination get front, delete front. Okay. So DQ, and call that the local variable x. All right. Now we reach this inner for loop that walks down the adjacency list of x. So for all y in adjacency list of x. So you know how to traverse an adjacency list in this list now, right? You just, like, move front, use the cursor, move front, while index greater than or equal to 0, move next, right? Or you could put all that in the heading of a for loop. I don't care if it's a for loop or a while loop when you go to write it. So you get what's under the cursor, or what the cursor is under, rather. Call that local variable y. So what do? So we're supposed to now discover y. We're discovering all the neighbors of x. If color y is white, that means it hasn't yet been discovered. After all, just because I'm discovering y as a neighbor doesn't mean that it wasn't discovered from some other direction before. I only want to discover new things. If y is undiscovered, then discover it by coloring it gray. Set its distance to be one more than where I discovered it from, and set its parent to be where I discovered it from, and then push it onto the back of the queue. That's the inner for loop, and that basically just, I speak of this for loop as processing the adjacency list of x. Once that for loop is done, I'm done with x because I've discovered all of its neighbors, all of its as yet undiscovered neighbors. At that point, we color it black, and we go to the next iteration of the while loop. If there is something in the queue at this point, there's more to do, because there's more stuff that's been discovered all of whose neighbors haven't been discovered, or at least we haven't proved that they've been discovered yet. Okay, well, I think this is time to do an example. I consider this a lot easier than PA3 because I didn't give you any algorithms. I just kind of waved my hands and I talked my way through dot product and add and stuff like that. But here's the actual algorithm. You can just translate this into valid C code. And that's your task in writing BFS, and it's not too difficult. Question? Oh, well, how do we get out of the while loop if I just NQ'd y? Because eventually, this y is going to reach the front of the queue, and it's going to be DQ'd. Do you see what I'm saying? I mean, I start by popping off the front of the queue, whatever's at the front. Then I push a few things on the back. Then I pop off whatever's on the front, and then I push a few things on the back. Then I pop off whatever's in the front. Then I push a few things onto the back. Well, eventually we're going to discover everything that's discoverable or reachable from the source. So I'll pop a vertex off the front, and there'll be nothing to push on the back. And I'll pop another vertex off the front, and there'll be nothing else to push onto the back. And that's how the queue will eventually get empty, and that's how this while loop will eventually end. Does that make sense? I beg your pardon? No, it will not error when it ends. It just ends, and that ends the algorithm. It's not an error for it to end. It's an error for it not to end. It better end, right? All right, so let's do an example. That was page 4, so this is page 5. Actually, let's do that. So here's an example of a graph. Call it G. This is the graph that is pictured on the front of the project description for PA4. This is nothing special. It's just some graph I made up. Labels. Vertex labels start at 1. They end at n, where n is the number of vertices. So I suggest that all of these fields, color, D, P, and adj, in your graph struct, be implemented as arrays of length n plus 1. So you blow off index 0. Don't use index 0. And that way, index 1 in the array is going to be the adjacency list, the adjacency array, I should say. That's going to be the adjacency list of vertex 1. And index 2 is going to be the adjacency list of vertex 2. Okay? If you do it some other way, and if you insist on using index 0, then you'll probably have it off by 1 error somewhere. So let's take the source in this run of BFS to be 3. The source can be any vertex. These are the inputs. This graph represented as an adjacency list, and the input, the source vertex, rather. Well, let's start by writing down the adjacency list representation. So think of this as an array, and the vertex labels are the indices to the array. So what's adjacent to 1, 2, and 3? What's adjacent to 2? 1, 4, 5, 6. What's adjacent to 3? 1, 4. 4 is adjacent to 2, 3, 5. 5 to 2, 4, 6. And 6 to 2, 5. Okay? So that is the adj array, the array of lists. What else do we have to keep track of for every vertex? We have to keep track of color, distance, and parent. Okay? So this is really what the algorithm does. It fills in, I guess your graph constructor, your constructor is going to make an empty graph, right, with just bare vertices. Then you're going to call add edge a number of times, and that's going to populate these adjacency lists. Think of add edge as similar to change entry in PA3. I hope you see now the similarity between PA3 and PA4 and PA5 also. Anytime we're using the adjacency list representation of a graph, you know, it's the underlying major data structure is an array of lists. Okay, so the colors are initialized to white, 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 white. The colors other than the source, 3. The distances to infinite, 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 infinite. The parents to nil, 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 nil. Those are the initialization values. Then we initialize the source to gray, 0, also nil. And now we also keep track of the Q. Let's write down the Q. Q is initially empty. Okay, let's run the algorithm. Or actually, we're up to line 9 now. I did all the initialization. So let's do the loop, 10 through 18. Well, the first thing I do, forgot to do 9. I've got to NQ the source. So 3 sits in the queue. Okay. Now I'm ready to enter the while loop. Q is not empty, so therefore I can enter this while loop. dqq, so x becomes 3. All right, temporarily the q is empty at this point. So x is 3. Now I'm supposed to traverse or walk down the adjacency list of x. The adjacency list of 3 is 1, 4. So this inner for loop has 2 executions, y equals 1, y equals 4. Okay. So first I look at 1. Has 1 been discovered? No, it's not, because it's white. So this conditional is true, so I color 1 gray. I set its distance to be 1 more than where I discovered it from, so I add 1 to this 0. And I set its parent to be where I discovered it from. That's x. That's 3 in this case. X is 3, you recall. And then I NQ 1. So now the Q is not empty anymore. All right, next iteration of this for loop, that takes care of this guy. Next iteration, y equals 4. When y equals 4, I ask, has 4 been discovered? No, because it's white. So we set its color to be gray, its distance to be 1 more than the 0 that I'm discovering it from 3, which has distance 0. So 0 plus 1 is 1. And I set its parent to be where I'm discovering it from. That's 3. Okay, that completes the adjacency list of 3. So this inner for loop is done. The only thing left is to color x, that's 3, black. Oops, I forgot to do something, didn't I? I forgot to NQ the 4. I always do this. I forget something. Okay, so I NQ'd the 4. Now I'm done with the first iteration of the outer while loop. The Q is not empty, so I extract the 1. X is now 1. So I have to traverse or process 1's adjacency list. Has 2 been discovered? It's going to go a little faster now. Has 2 been discovered? No, it's not, because it's white. So I color it gray, set its distance to be 1 more than where I'm discovering it from, so the 1 plus 1 is 2. Set its parent to be where I'm discovering it from, that's 1. And I NQ the 2. Okay? That takes care of the 2. And now the 3. Well, has 3 been discovered? Yeah, 3 was already discovered. It's not white because it was the source, right? So in that iteration of the inner for loop, this conditional turned out to be false because we'd already discovered 3 on the first step. So there's nothing left to do. We've been through the adjacency list of 1. So the only thing left to do is to color 1 black and go back to the top. So is the Q empty? No, it's not. So I extract the 4. 4 becomes X. Now I process 4's adjacency list in this inner for loop. Has 2 been discovered? Yes, it has. Has 3 been discovered? Yes, it has. Has 5 been discovered? No, it hasn't. 5 is still white. So I color it gray, set its distance to be 1 plus 1, which is 2, and set its parent to be where I'm discovering it from. That's 4. And I also NQ the 5. Don't forget to NQ. That takes care of the 5. I'm now done with 4, so I can color it black. Is the Q empty? No, it's not. Pull off the front of the Q. X is now 2. Process 2's adjacency list. Has 1 been discovered? Yes, it has. Has 4 been discovered? Yes, it has. See, these are now becoming false a lot of the time. Has 5 been discovered? Yes, it has. Has 6 been discovered? No, it hasn't. 6 is the only one that's still white. So I discover it by coloring it gray. I set its distance to be 1 more than where I discovered it from. Discovered it from 2. Its distance is 2, so this guy has distance 3. And I set its parent to be where I discovered it from, namely 2. And then I enqueue the 6. I didn't forget that time. So that takes care of 6. That takes care of the adjacency list of 2. So I'm done with the inner for loop when x equals 2. All I have to do is color 2 black. Is the queue empty? No, it's not. So I pull off the 5. 5 is x. Process its adjacency list. But 2's been discovered, 4's been discovered, 6 has been discovered. Nothing to do. Nothing more to discover from 5. So I color it black. Is the queue empty? No, it's not. So I pull off or dequeue the 6, process its adjacency list. 2's been discovered, 5's been discovered, color it black, and now we're done. Because the queue is empty. Okay, it's a good idea to keep track of, or draw a picture while we do this, of the BFS tree that is encoded in these parent pointers. Every vertex knows who its parent is. So here's the BFS tree that I'm speaking of. First of all, the root is the source, 3. And then, who has 3 as parent? That would be 1 and 4. And let's see, who has 1 as parent? 2. Who has 4 as parent? 5. Who has 5 as parent? Huh? Nobody. I know there's another vertex here. Who has 2 as parent? 6 has 2 as parent. So the parent of 6 is 2, parent of 2 is 1. All right, so this encodes shortest paths. Notice that if I just look at the distance for each of these vertices in this tree, the distance is nothing but its level in this tree. So depth 0 is the only vertex of distance 0 from 3, namely 3. 1 and 4 are distance 1. 2 and 5 are distance 2. And 6 is distance 3. So, the whole thing could be done if I just keep track of, I could keep track of the distance in the parent fields, or I could just draw this picture as I go. All right. Well, BFS works exactly the same way on a directed graph. Let me put this up here so we can still see the algorithm. Let's look at another example. I suggest you do a number of these examples by hand before you write BFS, so you're really sure of, how the function BFS is supposed to manipulate the graph struct itself. It's supposed to manipulate it by filling in this table, which means filling in a bunch of arrays. Okay, so nothing different. That's the beauty of this. You don't have to, it's not different code. The code is identical. Everything is the same, except for the adjacency list representation. So let's take G to be this directed graph. Okay. Labels. 5 vertices. Let's take the source this time to be 1. By the way, exercise. There's nothing special about the source 3. Take 5 as the source. Take 6 as the source. You know, rerun BFS yourself on the same examples with different sources. All right, so let's first draw the adjacency list representation of this graph. I guess I'll cover up the algorithm. Remember, in the directed graph version, I don't list everything adjacent to a vertex, but everything that is the terminus of a vertex having 1 as origin. Sorry, of an edge having 1 as origin. So look at 1. There's only one edge having 1 as origin, this edge, and its terminus is 4. How about 2? There are 2 outgoing edges from 2. They go to 1 and 5, respectively. What about 3? 2 outgoing edges to 2 and 5. And what about 4? Outgoing edges also to 2 and 5. And what about 5? No outgoing edges at all. So no edge has 5 as origin. So its adjacency list is empty. That is edge. I'll tell you what, let's go be a little bit more economical. I won't bother with the color. I'll let you guys keep track of the color. If you think about it, we could get rid of the color in this algorithm. Right? Because all you really need to know, what's the color used for? All you really need to know is whether a vertex has been discovered or not. And you can tell that by looking at its D field, for instance. Nevertheless, when you implement it, I do want you to have a color field and do want you to test the color field. So there are different ways to write this algorithm. So let's just keep track here of distance and parent. Let's keep track of the Q, and let's also write the BFS tree as we go. The Q starts with the source, and the BFS tree has the source as its root. So let's see, distances are 0, infinite, 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 nil, 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 nil. I'm just skipping the colors right now for brevity. Okay. So we extract or dequeue the 1 and process 1's adjacency list. Has 4 been discovered? No, it hasn't. So its distance is 1 from 0, or rather from 1, and its parent is where I discovered it from, 1. So the parent of 4 is 1, and there's going to be only one child of 1. So that's my BFS tree. Now what? Got to NQ the 4. Is the Q empty? No, it's not. So pull that off and process 4's adjacency list. 2 has not been discovered. So 1 plus 1 is 2. Its parent is 4. And we NQ it. Is that right? Am I forgetting something? Color, distance, parent, NQ. I'm skipping color. Distance, parent, NQ. All right. Next thing on 4's adjacency list after the 2 is the 5. Maybe I should underline. I got through 1's adjacency list. I'm on 4's adjacency list. 5 has not been discovered. So 5 is, its distance is 0 plus 1, which is no. Where am I discovering the 5 from? From 4. 1 plus 1 is 2. There we go. Sorry, I got confused for a second there. And so what is its parent? Its parent is 4. So 5 is a child of 4. And then I enqueue the 5. Okay, now is the queue empty? No, it's not. Done with the 5. So pull off the 2 and process 2's adjacency list. 1's been discovered, 5 has been discovered, so there's nothing to do. I color it black, but I'm not keeping track of the colors. So is the queue empty? No, it's not. So pull off the 5, process 5's adjacency list. There's nothing in its adjacency list, so nothing to do here. All right, the queue is now empty. The algorithm ends. But what vertex was not discovered? 3. And why? What happened? Why didn't we discover it? It's not reachable from the source. There is no way to get from 1 to 3. Notice all of the directionality of the edges is itself encoded in the adjacency list representation. So we can't get from 1 to 3 along a directed path. So reachability means reachability, in the directed case means reachability along a directed path. Can't get there. Can't get from anywhere to 3. Okay, and the distances, as before, are the depths in this tree, 0, 1, 2. In both cases, I really am looking at a subgraph of the original graph. So 3 to 1, so there's an edge in the subgraph. There's an edge in the subgraph. 1 to 2. 2 to 6. And 4 to 5. So this is a tree that sits in the original graph. It spans the connected component that includes the source. Spans means it includes all vertices in the connected component containing the source. Well, this is a connected graph, so there is only one connected component. And it gives shortest paths. I mean, here's a shortest path from 1 to 5. 1 to 3 to 4 to 5. Uh-oh. Did I do something wrong? Oh, my source is 3. Sorry about that. Got mixed up. This one, the source is 1, and this one, the source is 3. So our shortest path, yeah, look at this. There's 2 shortest paths that you can easily, actually a bunch of shortest paths. 3 to 4 to 5 to 6, right? That's the shortest path. 3 to 4 to 2 to 6, that's the shortest 3-6 path. And 3 to 1 to 2 to 6, that's the one we found. That's the one that BF has found in this case. In this case, 1 to 4 to 2, 1 to 4 to 2, that's the shortest 1-2 path. And 1 to 4 to 5, that's the shortest 1-5 path. And I think they're basically unique. But that's an accident that the shortest paths are unique in this example. All right, so the nice thing about this is, well, first of all, you see that reachability in the directed case looks different than reachability in the undirected case. Also, when you have multiple shortest paths, you're going to pick out one. Which one do you pick out? Why didn't we pick out 3 to 4 to 5 to 6 in this example, for instance? Well, we might have if we had processed the adjacency lists in a different order than I did. So notice when you go back to the pseudocode, there's nothing on line 12 that tells you in what order you're supposed to process the adjacency list of X. And the order that you pick in which to perform this for loop is going to ultimately affect which shortest paths you get. Change the order, you could get different shortest paths. I don't know if you can get every single shortest path by assigning some order to these adjacency lists, but you will get, in general, different shortest paths. All right, so that means that when you're running BFS, the answer you get and the output file that you generate depends on the order in which these adjacency lists are listed, or the order in which they are processed. So therefore, we need a convention so that my output file and your output file look identical. You've got to get the same shortest paths that I get in order for us to be able to test your program correctly. So our convention is that adjacency lists are going to be sorted by vertex labels. Smallest vertex label first, largest vertex label last. That's our convention. You are required to adhere to that convention. Sort adjacency lists by increasing vertex labels. With that convention, if you do that, I'm going to get the same, let's put it this way. The shortest path that you find is uniquely determined by this convention. This is very similar to what you already had to do in PA3, right? You had to maintain your entries in column sorted order. So now you're maintaining an adjacency list in sorted order. And so becomes the job of addEdge. So the addEdge function is supposed to, addEdge xy puts x on the adjacency list of y and y on the adjacency list of x. So it does two things. It does two insertions. And it's supposed to do an insertion that maintains sorted order, sorted by vertex label. By the way, addArc is what you would use to create a directed graph. So notice, what I'm trying to get you to build is a graph ADT that has multiple uses. We're only going to be in this project using, or the top-level client you're building, you're only going to be using addEdge because you're building an undirected graph. It's encoded in an input file. So you'll only be calling addEdge, but you're required to write addEdge and addArc. addArc xy adds y to the adjacency list of x, but not x to the adjacency list of y. So it creates a directed edge. Could you call both addArc and addEdge on the same graph? Yeah, you could do that, but this model, this ADT is not supposed to be modeling those kinds of mixed structures. There is a use for those kinds of mixed structures in discrete mathematics, but we're not trying to model them with this. So consider yourself to build, the client is either only calling addArc or only calling addEdge. And you don't need to enforce that at the graph ADT level. It's just up to the client. Question? I bet I know what the question is. You want me to guess what the question is? How is addEdge supposed to manipulate the size field versus addArc? Was that your question? Okay. See, I've taught this course so many times. That's got to be the millionth time I've heard that question. See, I already know what you're thinking. That's scaring even me. This will open up a mind-reading act or something. Okay, so for that reason, since it's the presumption in the design of this ADT module that the client is only building a bunch of undirected edges, or only creating a bunch of directed edges, that it really doesn't matter that they be compatible, right? So add arc should add 1 to size. Add edge should add 1 to size. Even though it's effectively, if you think of add edge as 2 calls to add arc, it would add 2. So many people like to, first write add arc, because that does one step, put y on the adjacency list of x, and then call add edge, simply call add arc twice. Builds the right structure. So you can do that, but then if add arc added 1 each time it was called to size, then add edge would have to subtract 1 from size because it added 1 too many. Does all that make sense, what I just said? Okay. So in an undirected graph, size is the number of undirected edges. In a directed graph, size is the number of directed edges. That's what we need to have. We've got 2 minutes left. I just want to show you in these 2 minutes one more way to run BFS, in which I don't have to write down the adjacency list representation. So there are the vertices. I put the labels in circles. Here are the edges. You can do this very fast without ever looking at the adjacency list representation and fill that in last, fill that in afterwards. So let's take this to be G and the source to be 3 again. Source is 3. Color it gray. Here's the Q. Here's the tree. So, color it gray by putting another circle around it. And then discover its undiscovered neighbors. And we discover them in increasing order by vertex label. So we discover 2. And I discover 6. Okay. And I put circles around them to make them gray, right? And then this one becomes black. Cross it out. And then go to the next one, 2. Discover its undiscovered neighbors, which are 1 and 5, in that order. And there, so I'm done with 2. The next thing in the list is 6. Discover its undiscovered neighbors. Notice 5's already discovered, so it's only 8 is the only child of 6. So it becomes gray, 6 becomes black. Next thing in the queue is 1. Its undiscovered neighbor is 4. It becomes gray, 1 becomes black. Next thing in the queue is 5. It has no undiscovered neighbors. It's just gone, doesn't have any children. Next thing is 8. 8 has 2 undiscovered neighbors, 7 and 9. I didn't leave anything out of there, did I? Yeah, okay. 7 and 9, those are children of 8. 8 is now black. Oh, 5 is now black, sorry. And then 4 has no undiscovered neighbors. 7 has no undiscovered neighbor, so no children. 9 has 1 undiscovered neighbor, 10. 9 is done, and 10 has no undiscovered neighbors. Everything's been discovered, and these are the distances. 0, 1, 2, 3, 4. So I can now fill in the table from all this information. So fill in the table last. That's a really good thing to be able to do on an exam. Sorry I went 2 minutes over. I predict that you'll have to do something like this on an exam. I'll see you Friday. We'll talk about DFS, depth first search. Did I do that right? 3, 2, 6, 1, 5, 8, 4, 7, 9, 10. Yes. Go ahead.